Degree in radian mode. So you got to know your calculator. The cosine 30 degrees on your calculator versus if you put it in wrong, you got to be smart about the answer you get. I'm going to do it wrong. I'm going to use radian mode, and I'm going to type in cosine of 30. If you go cosine of 30 degrees in radian mode, I get 0.153. So as you go along, start thinking of what answers make sense. And if you remember, we're going to use the unit circle here in 2 shakes. If you remember, the actual cosine of 30 degrees is the square root of 3 over 2. Then that answer 0.154 that you get on there doesn't make sense. Start thinking in terms of, man, that doesn't seem to make sense in the context of the problem, so maybe I have it in the wrong mode. And that's usually a good way to fix your results. And by the way, this cosine of 30 degrees on your calculator still is pretty wonky in degree mode. I get, according to calculations, 0.866, but it's actually the square root of 3 over 2. That's the approximator, that's the squiggles, but the real cosine of 30, which we're going to do now in the unit circle, is square root 3 over 2. Okay. And then 158, sine of 158. When we get to it, we're going to start talking about cosine and sine being like heights and widths within the unit circle. We kind of started to hint at that before. Just make sure your mode is correct. That's all that this is there for. There's nothing much to do. Tangent of pi. Did you know in your calculator there's a pi button? It's right above the caret symbol. If you look above the caret symbol, there's a pi. And if you want to do the tangent of pi, tan, that's a radian. And nobody's telling you it's in radians, but you are the one that says, ooh, that's a radian. So I got to go to radian mode on my calculator. If you put in tangent of pi in the non-radian, you will get the wrong result. And usually you can reason it out and figure out why it's not right. So tangent of pi happens to be 0. Ooh, that's something we got to learn on the unit circle too. Okay. So calculators, be careful. Inverse trig in degree mode looks like this. Let me go to the next page here. So inverse triggy trig. When you guys are trying to find an angle, you know that the sine of theta is 3/7. To undo sine and get theta by itself is what we want. Think of it algebraically. There is an undoing of sine. It's called sine -1 or sine inverse. You take it at both sides. And it cancels the sign on the left, and you get theta equals the inverse sine of 3/7. There's a button for it on your calculator. It's second sine. This one, you just have to make sure what mode is dictated by the problem, or somebody's going to say degree mode, or all the givens are in degree, or something like that. This one says degree, right up top. See it in my...
Why did you have 3 fifths?
Because 7, I don't know, 7s are unlucky, maybe? Thanks, Carter. That's what I needed. I goofed it up. Theta. Inverse sine of 3/7, and you get an answer, and make sure it makes sense. Like, inverse sine of 3/7, we're going to go back to triangles here in a second. Do you guys remember from our conversation last week that sine is opposite over hypotenuse? I'm sure you remember this. In SOHCAHTOA, it's opposite over hypotenuse, 3/7. And when I take the inverse sine, does an angle that spits out from my calculator make sense? When I go second sine 3/7 and hit Entrée s'il vous plaît, I get 0.44. How's that sound? Does that look like 0.44 degrees? That's like less than 1 degree. No. So you realize, oh, dang it, I'm in the wrong mode. Because I can tell just by looking, if I know the sine of theta means the opposite over the hypotenuse is 3/7 ratio, then I must be in the wrong mode. So you go mode degree, you fix it, Entrée s'il vous plaît, you go second sine, 3/7, and I get 25.37 squiggles. I'm gonna go 378 or 376, 338 we'll call it. But make sure this is the part where you can see in general, because Tristina said something about like you can actually physically see it in the real world. Trig sine of theta equals 3/7 has a representation you can actually draw, and then you can decide if your answer is even reasonable. I love that about trig. It's like physical. It's cool. Okay, tangent. Should we try another one? Tangent of theta is pi over 4. Now I'm going to draw theta in a corner, and if I say it's pi over 4, there's 2 ways you could think about it. That's opposite over adjacent, and if you're wondering where I got that Remember, SOHCAHTOA helps you remember the ratios of each trig function in particular. The pi over 4, you could either say pi over 4 for your opposite over adjacent, that's fine, or you could actually write it with pi over 4 and 1 is this one. This one's a bit confusing, but it's just telling you those are both okay. They're actually the same shape of triangle. There's just different sizes. The top one would be bigger. I didn't draw it that way than the bottom one because this leg is 1 and the height would be pi over 4. 4 long and pi tall. But either way you cut it, 3.14 over 4, the angle here better make sense. If I go second tangent and I'm in the wrong mode, this one is still in degree mode. If I go second tangent and I'm in radian mode of pi over 4, typing it in, I get nothing other than, say tangent again, 0.66. And that makes no sense. That's like less than 1 degree. So you realize, dang it, must be in the wrong mode. So you go over there, in context, hit degree mode, and you run it again. Got it. 38 degrees, roughly. 38.15. Those are the things that are different from what you already learned, is that kind of double check your answers, make sense of it. There's time to do that. Because a lot of this is review for y'all. You're trying to get it a little better than you got it before. And make sense of some stuff. Okay, next page. Flippity flip. It's this. Y'all got SOHCAHTOA there in case you didn't get it the first time. There's this question of evaluate the other 5 trig functions. And when I say evaluate the other 5 trig functions, and I give you sine of theta is 5/6, when you're given a ratio, a sine of theta equals some number, that allows you to draw in the appropriate sides of 5 is your opposite and 6 is your hypotenuse. And it gives you a physical picture to draw from. You could go get the adjacent with a little Pythagorean theorem, and you're going to want to, because the next thing is find the other 5 trig functions. Be careful of your Pythagorean theorem. I'm going to call this x for right now. Let me put it in there and it's all x. But I would do x squared plus y squared is c squared is your classic Pythagorean theorem, where the c is the hypotenuse. The thing is, it's not 5, biggest error is people put in 6 squared plus 5 squared equals, and they get to be careful. The x is your horizontal distance, and I don't know it. Y is 5. And the hypotenuse is always the longest of the 3 sides in a right triangle. So keep that in mind. Hypotenuse will always be longer than the other 2 sides of a right triangle. So, in fact, the only way we're going to get x squared is now we're going to subtract 5 squared from both sides. I'm sure you found it a long time ago. But x squared equals 36 minus 25, so 11. And you get your x is, and you have to square root both sides, x is equal to, usually we'd put plus or minus the square root of 11, but these are currently, later on, we will use the positive and the negative. It's a true story, because we'll have triangles that actually are plotted in the coordinate plane. So when I do that later on, when I draw in like a coordinate grid, and we talked about sine of angles, they can actually take on negative. I could draw this triangle facing the other way. It could still be 5 and 6 here, but on the left-hand case, it'd be negative square root of 11 because you'd be going left. It's drawn in a coordinate grid, so this would be like 0, 0 right here in the origin. And negative square root of 11 just means going left on the grid. So that's the only time it makes sense. Its length is square root of 11, but negative is talking about a direction that you're walking on that particular units, or the coordinate grid. So this would be negative square root of 11. Isn't that weird? It makes sense if you graph it, but we all know if I'm actually talking about a physical triangle, it's only going to be positive square root of 11. That would make sense. Okay. Now, it says, evaluate, it says, let theta be an acute angle such that sine of theta is 5/6. Evaluate the 5 other trig functions of theta. Now, there is a little problem with this particular problem. It doesn't, since both of these triangles work if I'm drawing on the coordinate grid, there's usually a clue that they give you that helps you specify which triangle are we talking about. Are we talking about the one on the left? Are we talking about the one on the right? And there's always this extra clue. It happens in the example down below. But somebody will probably say the clue would be in the first quadrant. That would be helpful. Because then they say, oh, that means the one on the right, first quadrant. Do you remember the first quadrant? The quadrants go in counterclockwise order. There's 1 is in the upper right, 2, 3, 4 counterclockwise. Okay. Lots of things to remember. But if I do that first problem, now that I go in and label it, the other trig functions are cosine of theta, and the other cosine and their co-functions, which we'll do in a minute. So cosine of theta will go fine. We need to do tangent of theta. Okay, but we already have sine of theta. That was the one that was given to us, which was 5/6. Cosine of theta is the adjacent over the hypotenuse, and since we're doing the first quadrant one, it's square root of 11 over 6. Okay, and I'm going to go ahead and zoom in on this so you guys can see it. And then tangent of theta would be that opposite side of 5 over square root of 11. Okay, so it's opposite over adjacent. The other functions are the co-functions. So sine of theta is 5/6, then its co-function is, do you remember the co-function for sine? Cosecant. Ooh, you do, it's good. It's been cosecant of theta is the co-function, and you just flip it over, so it's 6/5. Okay, so those two go together. And then cosine has secant, and for whatever it is, I think those can be easily mixed up in your brain, so you got to find a way to memorize that part of it. And secant would just be cosine over upside down, 6 over square root of 11. And it's okay if you have that square root in there in the denominator for now. We'll talk about rationalizing later. We did first semester, or first term, but we'll talk more later. And then tangent of theta is cotangent theta. And that's square root of 11 over 5. Those are the 6 trig functions you can write. So anytime you draw a triangle in the coordinate grid and it says name all the trig functions, you can name 6 trig functions. It's just all the different ratios of sides. They just have special names. Okay, so there you are. And then the bottom one, same thing. I'm not going to get in too many details, and we'll wrap it up so you can play a little bit. But cosine of theta is 2/7, and sine of theta is less than or equal to 0. Here's the deal. I can draw a triangle with theta in a corner, and adjacent over hypotenuse is cosine. So you realize that's 2 and 7. So that'd be the sides they gave me. There's another way I could draw this and still have those sides if I do it in the coordinate grid. Okay, and I think I didn't give myself enough room on here. So I'm going to draw it on the next page. I'll just add one to it. Hang in there, ready? It's just on a clean page. So what I just drew is this one. This is 2/7. Not drawn to scale at all. But did you realize you could draw this another way and still have those sides? You could do 2/7 this way and have theta down below. If you do the coordinate grid, and you graph your triangle in it, which we often do, both of those triangles, cosine of theta is 2/7. The 2 that you see here is the same length on both of them. The hypotenuse is 7 in both cases. Some of you might wonder, why didn't I do it to the left? Could you draw it facing the other direction? How about this one? Could I do 2 on this side? Maybe 2 here in 7ths. The problem with this one, bless you, is that if you go left on the coordinate grid, that would have a -2 anytime. There's direction associated. When you put triangles in the coordinate grid, direction matters. To the left is negative, to the right is positive. So that doesn't work. So it's one of these two scenarios. Cosine of theta is 2/7, could be these two triangles, and then they hand you a clue. They say that the sine of theta is greater than or equal to 0, is it? I think. Can't remember if it was, or it's less than 0. Less than 0. So the sine of theta is less than 0, and if that's given to you, one of these two triangles meets that requirement. So of these two triangles, which one has a sine that's less than 0? Sine would be the opposite over the hypotenuse. So opposite of our hypotenuse would be something over 7 on the top one. In the bottom one, it would be negative something because it's facing down. So isn't that kind of goofy? So let's call it y. The one down below would be negative y because it's anytime you're graphing in a grid, direction negative means left or down. So of the two triangles that I could draw where the cosine is 2/7, I have to choose this one, means the bottom one. Cool? So those are interesting things about trig that you might not remember is it represents sides. What we add to the mix is that we'll start graphing those triangles in the coordinate grid where it's xy coordinate grid. Negative numbers mean left of the origin or down from the origin. Positive means up or to the right. And it makes a difference. So what we end up with is that bottom triangle, not the top one, so we can nix it on top. We're going to circle that one down on the bottom. We need to find the sides, all three sides. So I need to find y, so it's a little Pythagorean theorem, and then you're home free. So you got 2 squared plus y squared equals 7 squared. Not 7 squared, it's not 2 squared plus 7 squared equals y squared. Be careful, it's always the hypotenuse is always that longest side. It's always after the equal sign, the hypotenuse is always over here. It's never within the sum inside here. So then y squared equals 7 squared minus 2 squared. And then we get y is plus or minus the square root of 49 minus 4, so it's 45. We'll simplify that a little bit, but you realize it says plus or minus because it's talking about it could have been both of these values. Both of them are possible. But we were given a clue in the beginning that says we have to focus on that bottom triangle rather than the top one. So we're going to eliminate, we're going to cross out that negative. I'm sorry, cross out the positive and stick with the negative. Square root of 45. That's our other side. Now some of you want to simplify that, and you should. It's square root of 45 is also known as, if you factor out, there's a 9 times 5. It is 3 square roots of 5. So we can use that too. So you can totally simplify those. So let's do our 6 trig functions. I'm going to add a page because I need some room. Okay, so if I do it all together, this is what I've got. Here's my triangle. Bam, bam, bam. 7, 2, negative 3 square root 5. And if I do my 6 trig functions, I got cosine, of course, is 2/7. And then sine of theta is negative 3 square roots of 5 over 7. Tangent is, what is it, negative 3 square roots of 5 over 2? Opposite over, so opposite over adjacent is relative to where the angle is, so opposite over adjacent, sitting next door to it. And then when you do the cofunctions, you flip it over. So secant would be the reciprocal cofunction of cosine, so it's 7/2. And then cosecant is the reciprocal of sine, so negative 7 over 3 square roots of 5. And I'm not rationalizing right now, definitely on purpose. And then cotangent is just flipping those over. Negative 2 over 3 square root of 5. So it flips it over. So triangles in the coordinate grid, negatives mean something. They actually count left or down as a dimension. Okay, they were drawn from the origin. So this is called, I'm going to flip, I don't know if it's in your note packets or not. Let me check it out. It's called a reference angle. Reference triangles, I kind of put it in there. But I'm going to just add it on as my own little extra page. The thing is you can draw any triangle in the coordinate grid facing any direction you like. So there's, so a triangle of a certain dimension. So I cut out a triangle out of paper, and there's 4 ways I could orient it on my grid. I could draw one of these 4 ways. Okay, so I cut out this little paper triangle and I lay it down. Okay, and the ratio of the sides is the same no matter how I draw it, so it looks like one of those TIE fighter things. You can make it something cool. But those are your 4 possible triangles. The way this works is we call the angle, you place the triangle so that the reference angle, this is called the reference angle, is always touching the x-axis. So that reference angle is always butted up against the x-axis. And it's against the origin and the x-axis. So if you don't do that, that could mess up how you lay your triangle. But notice it always touches the x-axis. It always rises from the x-axis. That theta has to either descend from it, like angle down from the x-axis, or angle up. But the theta itself must touch the x-axis and the origin. It's called the reference angle. So those are the reference angles. It helps you orient your triangle if you put it in all four corners. Touch the x-axis and the origin simultaneously. They have to. So when you're drawing it, the mistake that could be made is if you draw a triangle in here and you do like this kind of thing. You stick your triangle in like this and put theta like that. No, don't do that. Okay, so that's the difference, is the reference angle. That angle right there is touching the origin, but it's not touching the x-axis. So it's got to touch both. Another no-no is you can't draw it so that it's like a weird-looking backward-facing right triangle like this. Theta in the corner there. It's touching the x-axis, but not the origin. No, it has to touch both. No. Okay, that's enough to kick you into high gear on the rest of this thing. I'm going to hit stop.